up. Recording is in progress. Unfortunately, this is the last talk of this scientific committee meeting of links. So I guess it will be one firework talk by Professor Kumar. Professor Kumar is a strong supporter of links. He's a frequent speaker at the links workshop. He's now a distinguished professor at Texas A&M. He's the chair of the College of Engineering. He has been previously in many positions in the US, and actually, I guess he has now emeritus or honorary status in all of those universities. If I had to list all his awards, it would be over time very soon. So I will shut down now and give the word to Prof. Kumar, please.
Thank you so much. I appreciate it. You know, it would have been, I cannot think of anything better than to end this 2.5-year curfew with a trip to Paris, but unfortunately I was not able to make the trip. So remote will have to do. So it's a pleasure to talk again. And this time I'm going to talk about reinforcement learning, exploration versus exploitation, etc. And these are all the people who have been working with me. Hsieh Lu is at Facebook. Ping Chun is a faculty member at National Chao Tong University in Taiwan. Hung is a student. Anirban is a professor in statistics here. Hsieh is a PhD student with me. And Rahul just took up a position at Indian Institute of Science in Bangalore. Okay, so the holy grail of control from 1950 onwards was adaptive control. Okay, I'm not sure. Okay, and the basic problem is control an unknown black box. So you want to design some controller so that when you hook it up, it works beautifully. Now, early on, it was noticed that control had two purposes. One is to excite the system to learn about it, and the other is actually control it to drive down the cost. And this was called by Feldbaum in the Soviet Union as dual control. And the fundamental question in control systems was that the overall adaptive control is highly nonlinear. So the system may be linear, but after you do all your nonlinear least squares and all these things, it becomes very nonlinear. And the first question is it stable? And this question kept the control field busy for about 40 years. And finally, things got resolved in the 90s, okay? Okay, and it was studied in several contexts: linear deterministic systems, linear stochastic systems, MultiArmed bandits, self-tuning controller, applied in industrial contexts, lots of industrial contexts, beginning with paper mills, aircraft, etc., etc., Markovian systems, and now reborn as reinforcement learning. Okay, so I'll connect all these dots. I'll try to connect. So let me start with the adaptive control problem for Markov decision processes. And basically, there is a state space. Let me see. Yeah. There's a finite state space, there's a finite action set. And given the action you take, the transition probabilities tell you where to go. And you get a certain reward depending on which transition. The whole issue is that you don't know these transition probabilities. So they depend on some unknown parameter theta. And that's what makes it adaptive control problem. All we know is that theta belongs to some set of unknown possible values. Now, for each possible value, if you knew it, there would be some optimal policy that you could apply, some stationary policy, some mapping from states into actions. Okay. Now, the true parameter is some theta 0 in the set capital theta, but you don't know what it is. Now, nevertheless, your goal is to maximize some long-term average reward. Okay, so there is the reward per step reward you incur, and you want to maximize it. Now, if we knew theta 0, we would apply the particular stationary policy corresponding to theta 0, but we don't know theta 0. Okay? So this problem was first addressed seriously by Peter Mandl in the then Czechoslovakia at Charles University. And Peter looked at the following problem, a certainty equivalent approach. he said, listen, we don't know the parameter theta 0, so I'll make a maximum likelihood estimate. Okay, let's call the theta hat. And then what I'll do is I'll pretend that that maximum likelihood estimate is correct, and I will do whatever, I'll apply whatever action would be appropriate in that case. Okay. And this is called certainty equivalence because you make an estimate and you assume that it is exact, it's correct. And the question that he asked was, does self-tuning occur? If you keep doing this, do these estimates converge to the true value, and do the policies then converge to the true things, and so on? And he gave a positive answer under highly restrictive conditions. In particular, he said yes, if there's a certain identifiability condition that holds. And the identifiability condition basically says that no matter what state you're in, what action you take, and what is you will, the outgoing transitions will differentiate between any two parameters. So you're always, at every movement, you're getting information that differentiates parameters, so you can actually figure out what's going on. But this condition is not satisfied even in, say, MultiArmed bandits. Okay. Now, this was then re-examined by Borkar and Varaiya in 1979. And they said no, the answer in general is no. And there's a fundamental closed loop identifiability problem in that you're trying to learn the system under closed loop, not open loop. And this is exactly the same as what is called the conflict between exploration and exploitation. Okay, so let me tell you Borkar and Varaiya's result. So they showed that if you do the certainty equivalence policy, your parameter estimates will converge to some random theta star. Okay, they converge to something. And under some conditions, the policies also will converge. Okay. Now, when it has converged asymptotically, the actual closed loop system looks like this. That is, the true parameter, the transition probabilities are under the true parameter, but the actions are under theta star. So this is the true closed loop system. This is what it's looking like. But the estimator thinks that this is what it is. The estimator thinks that the estimate theta star fits it. So I think those are the transition probabilities. And I know that this is the feedback you're applying. So it says this is what the estimator thinks. And if your estimator is any good, these two behaviors will have to be exactly the same. Otherwise, you'd be able to quickly say theta star is not correct. So at convergence, you get equivalence between these two. And this is called closed loop identification. You can identify the closed loop transition probabilities under the policy, but not the open loop transition probabilities, because there may be actions that you're not investigating under the closed loop. Okay. So to write it as a formula, the transition probability from I to J under the policy corresponding to theta star will be the same in the model theta 0 or theta star. And that's called closed loop identification. But unfortunately, this limiting control of phi theta star is not optimal for theta 0. So you converge to a suboptimal thing. So as theta hat converges, basically we stop exploring for better control laws. So this is the exploration versus exploitation issue. So in 1980, we looked at it, and with Art Becker, who was my second PhD student actually. And so this is what we found. We noticed that there was a certain inherent bias of this maximum likelihood estimate. So let V optimal theta be the optimal reward that you could squeeze out of the system if the parameter was theta. So for every model, there's an optimal reward you can get, call that V optimal. And now, because these two systems are equivalent in their behavior, the rewards they generate also are equivalent. Okay. Now, on the left, the reward that you get is suboptimal for theta 0. Why? Because for theta 0, theta star is not necessarily an optimal policy. So this left-hand side generates a suboptimal reward as far as theta 0 is concerned. So the actual reward is less than V optimal theta 0. On the other hand, for the right-hand side, theta star is optimal for theta star. So the reward it generates is exactly optimal. So what we then realize is that V theta star should be less than V theta, less than V theta 0. Okay. So in other words, there is a one-sided bias. Your parameter estimates will converge to something for which the optimal reward is less than that of the true value. So then we thought, hey, listen, so if the parameters have this one-sided bias, why don't we try to correct it? Can we reverse bias it to favor parameters with higher rewards and get the optimality we want? So we came up with what we called that time a cost-biased maximum likelihood estimate, because in those days we were all trying to minimize cost, but nowadays people are trying to maximize reward, which is the same thing. So we goes by either reward biased or cost biased maximum likelihood estimate, and this is the way it goes. So I want to bias the maximum likelihood estimate to favor parameters with larger rewards. So this is the standard maximum likelihood estimate. You choose a theta which maximizes the likelihood. Now what I'm going to do is I'm going to give a slight preference for models which have a larger optimal reward. But I'll raise it to power alpha t, which grows with t. Okay. Now, what we want of alpha t is that it should go to infinity as t goes to infinity, but it should do slowly. So alpha t should be little o of t. Okay. And it turns out that this does the trick. There's a delicate balancing act which is needed. This biasing term needs to be small enough that it doesn't damage the inherently good properties of the maximum likelihood estimator. So it can't be too big. On the other hand, it has to be large enough that it actually succeeds in moving the estimates towards parameters with a larger reward. Okay, and I'll give you a very rough idea, back of the envelope sketch, which is a lot of technical details. What I'm saying are not true, but they can be fixed. So I want to first show you that the bias is small enough. So what I'm going to do is I'm going to rewrite this maximum likelihood, bias maximum likelihood estimate by taking the logs. So I take the log of the bias maximum likelihood estimate, and this is what it becomes. Now, this term, this first term, grows like little o of t because alpha of t grows like little o of t. But on the other hand, the summation grows like t, and therefore this bias is small compared to the likelihood. So it doesn't damage closed loop identification. At the same time, it's large enough because if you write this as the maximum the likelihood ratio, in other words, you can divide this quantity by any constant and the maximizer doesn't change. And in particular, as long as you divide it by something that doesn't depend on theta, you're okay. So divide it in particular by the bias likelihood under the true parameter. Okay, this gives you the likelihood ratio. And now, if the numerator is less than the denominator, then as alpha t goes to infinity, this quantity will converge to 0. But on the other hand, the second term, at least for finite parameter sets, for every theta, this is a positive martingale. It converges, therefore it's bounded, it's positive, and this goes to 0. So if the numerator were less than the denominator, the overall ratio would go to 0. But for an optimizer, it has to be at least 1, right? Because you can always choose theta 0 as your estimate. Okay, so that means the parameters have to converge to something with a larger reward. And so the bias is just right, and phi optimal theta star is optimal for theta 0. So that's the rough argument to intuitively understand this. And you can prove the following theorem. Using this reward bias maximum likelihood estimate with certainty equivalence control, you can actually get long-term average optimality. And this thing was examined from 1980 to 1994 by us and a whole bunch of other people in variety contexts, MDPs, linear quadratic Gaussian systems, nonlinear controls, control diffusions, etc. Okay, so this long-term average optimality was established. But then, now the focus nowadays is not on long-term average optimality, it's on a much finer measure of optimality called regret. And that is something that I didn't pursue after that. So this regret was introduced by Lai and Robbins in 1995, actually 2-3 years after we had done this bias maximum likelihood estimate. And what Lai said was, hey, listen, I want to look at this thing called regret, which is how badly you are doing compared to what you could do with the best policy. So as t progresses, compare the total rewards that you've gotten up to that point versus t times the maximum reward. Okay, that's called the regret. And long-term average optimality corresponds to saying that this regret is little o of t, because in long-term average you divide by t, and when you divide by t, you if the regret goes to 0, then you get long-term average optimality. So Lai and Robbins asked a much stronger question: how small can we make regret? And they actually showed that you can make it as small as order log t, and they actually identified the precise asymptotic constant, which is related to the Kullback-Leibler divergence. So very beautiful result of Lai and Robbins, asymptotic optimality of regret up to log order. And they also identified a policy which gives you that asymptotic precise value with that constant. And this is called the upper confidence interval policy. So they said for each parameter, for each arm, let us say you're doing a multi-arm bandit case, okay? For each bandit, you obtain a confidence interval. Let us say I played a bandit 100 times and I got 70 successes, then I may have a confidence interval between 0.6 and 0.8, right? So choose the upper limit of that confidence interval, 0.8, and write down the confidence intervals for all the arms and play the arm with the largest upper value. So that is called the upper confidence interval or upper confidence bound policy, called UCB. Play the highest upper confidence bound. Now, what's the intuition behind this? So supposing you have not explored an arm enough, say arm 1 has not been played enough, then your confidence interval will be pretty large because you're pretty uncertain about it. So your upper confidence bound will be pretty large. Whereas if you've played something a lot, the confidence interval will be small, though its mean value may be high. So basically, it is also giving a weightage to exploring things more. Okay, so it's balancing this exploration versus exploitation by looking not at the center of the confidence interval, but by the upper confidence bound. And some arm is not explored enough. Its UCB will be large, thus preferring it. And this is now called the UCB policy, and it is known to every single person in reinforcement learning. Okay, this is the basic policy which everybody starts with. Okay, so nowadays this is called optimism in the face of uncertainty. Okay. Now, both the reward bias maximum likelihood estimate and the UCB policy embody the principle of optimism in the face of uncertainty, but in different ways. So in the reward bias maximum likelihood estimate, we directly give preference to arms or parameters which have a larger potential reward, right? And so it biases estimate towards, in the case of multi-armed bandits, arms with larger theta. Whereas the UCB policy of Lai and Robbins prefers arms for which there is a chance of a larger theta, okay? And actually, so recently, we can actually show that these are related in the following sense. RBMLE is a Lagrangian version, whereas UCB is a primal formulation. So UCB says, I want to maximize the reward subject to some bound on the confidence. Whereas now if you take this constraint and I join it, then basically you get, you take 1 over alpha. So put a lambda over here, then you will join the constraint, then take 1 over lambda, put it as alpha, and you get RBMLE. However, alpha t, it turns out that choosing alpha t equal to 1 over the Lagrange multiplier is not good, as we'll see shortly. So that's the kind of connection between them. Now, there has been lots and lots of testing of UCB over the past 15 years or so, as well as something called Thompson sampling, which goes back to the original paper on bandits, okay? And there has been no follow-up work on RBMLE, and in fact, the machine learning community is generally aware of this work, and even we didn't pursue this for 20 years. So what is the theoretical regret guarantee of RBMLE? How does it perform empirically? What can you say for more general systems and so on? That's what I'm going to talk about. Okay, so let's get back to the 21st century. And let's look at MultiArmed bandits. Okay. So currently, the empirically good policies for minimum regret are still Thompson sampling is still very good. What is Thompson sampling? It says put a prior on the arms and then play an arm with the probability that it is proportional to the probability that it is the best. Okay, so that's Thompson sampling. And UCB basically chooses the upper bound of the confidence interval. So that is centered around the empirical mean plus the width of the half width of the confidence interval, which is this. NT is the number of times you've played an arm, for example, in the case of MultiArmed bandits. And then recently, Ben Van Roy and his group at Stanford have come up with information-directed sampling, which is a kind of a heuristic. They say, listen, we need to do exploration, but we also want to do exploitation. So they said, how about maximizing the information about the optimal choice? That's what exploration is. And exploitation is to reduce the expected regret. So they said, I want to minimize the numerator and I want to maximize the denominator. So just form a ratio. So that's what is called information-directed sampling. And there is a modification of that, which we'll see in a second. Now, this is a policy that generally performs well, but it is extremely complicated to compute because there are very high dimensional integrals that you have to evaluate when you're calculating all these things. And they say that there's much more work to be done to design efficient algorithms for various problem classes. Okay, so question is, how does RBMLE perform? What's its order of regret? Is it also log T? How does it perform empirically? Actually, in practice, how does it work? How does the computation scale with the number of arms? And so that's what we examine. So first, I want to say that for many bandit families, you can actually get very simple explicit policies. So take the exponential family of distributions for bandit rewards, one parameter exponential family. And for Bernoulli bandits, we knew this in 1981. There's a very simple index policy. Let S be the number of successes in an arm, N is the total number of plays, F is the number of failures, S is the number of successes, alpha is your bias. Form the simple index, and if you just play that all the time, that's RBMLE. Very simple. For exponential bandits, also it's very simple. For each arm, look at the total reward you've gotten from it, divide it by the same thing plus alpha. And for Gaussian bandits, add alpha to the total reward and divide by the time. Very simple indices, okay? And the results are the following. If you choose alpha t equal to gamma t log t, where gamma t can go to infinity as slowly as you like, the regret will be gamma t log t. Now, if you knew the gap means the best between the difference between the best arm and the second best arm. Sorry. And you could choose your constant as a function of the gap. So you choose alpha t equal to c delta log t, then you'll get big O log t. But even if you don't know this gap, for Bernoulli and Sub-Gaussian bandits, you can estimate the gap and then you adapt it and you get logarithmic regret. Okay. How does it perform empirically? Now, so I will skip this. Okay, empirical performance testing. Now you must remember, Google gets about 90% of its revenue from basically a multi-armed bandit problem. It has to show you which hotels to display at the top right corner, right? So it doesn't know whether, I mean, the contract with Google is that if a person clicks on Hilton, not necessarily gets a room at Hilton. If he clicks on Hilton, then Hilton will pay X dollars to Google, and that is something that it has bid for. Now, of course, Google doesn't put the highest bidders in order because it doesn't know whether one hotel has such a bad reputation that nobody's ever going to click on it. And you really need to know how popular it is as well as how much money it's giving you to rank them. So it's a bandit problem. And okay, so this is a simple Bernoulli bandit. Here we have 10 bandits and they differ by 0.01 in their probability. So kind of a minute difference. And this is how the regret grows with time for various policies. So this is the RBMLE policy. This is the way it grows with regret. This is this dark black line is UCB. UCB actually doesn't perform very well in the small sample regime. It's only good for asymptotics. Okay. VIDS, which is the modification of this policy of Van Roy's group, seems to be pretty good, and IDS, they do pretty good. Okay, so this is how the regret grows. And the other, what I'm plotting here is now another metric, which is what is the computational complexity of implementing the bandit policy, because Google has to do very fast computation to decide, and it's got thousands of arms, thousands of hotels that it can put in the top right when you query for hotels, right? So what's the computation time? And I'm plotting the computation time on the log scale, and I'm plotting the regret, average regret on the x-axis here. Now, ideally, you'd like a policy that's over here. It has 0 regret and 0 computation time. Low left-hand count would be where it's optimal. Now, this is where RBMLE falls. This is where the VIDSS, the information-directed sampling, is orders of magnitude better, and the regret is also pretty good. Okay. These are various statistics. For Gaussian bandits, also same thing. This is RBMLE. These are the other policies. This again is UCB. And again, it's in the lower left. And this is for exponential bandits. Again, it's pretty good, and so on. Okay, now we've also looked at this in all the other reinforcement learning problems of interest, contextual bandits. So in contextual bandits, you get a context at each time, which is generated by an adversary, possibly. And you need to choose, and your reward is going to be a linear function of that context for each parameter. And you need to choose which arm to play, but you don't also know this theta, okay, which defines a linear function. Okay, so RBMLE's, this is RBMLE's policy. In this case, we add a small regularizer when estimating theta for least squares. Then we can show that we get square root of t log t regret, which is the best known regret so far. It's, I mean, shared as the best known regret by other policies. And this is the way it performs. So if you look at linear UCB, it is somewhere here. Not, sorry, linear UCB is, oh, where is it? I can't. This is linear RBMLE, which is somewhere here. Okay, it's pretty good. And again, if you do computation time versus this, it's over here. Okay, it's pretty good. Then Markov decision processes. So you take a Markov decision process, and if the gap is known, then with an epoch-based algorithm, we can also get log t regret. And this is how the regret goes. If you compare it with the 2 leading contenders, this is RBMLE. This is UCRL2, an upper confidence bound policy for reinforcement learning. This is the green, red line. And this is Thompson sampling, which still persists to this day. So again, RBMLE seems to do pretty well. And this is for different sizes of systems with 20 states, 20 actions, 50 states, etc. In all cases, RBMLE seems to do pretty well. And then most recently for linear quadratic sub-Gaussian systems. So take a linear quadratic system with a sub-Gaussian noise, and then take a quadratic cost, okay? And here now we define a slightly modified version. We're not able to actually theoretically analyze RBMLE as is. So what we actually do is we take this Lagrangian corresponding to RBMLE, but we also take the constraint corresponding to UCB. So it turns out that even though this constraint is not active, by putting it in, I can actually analyze it, okay? So it's in fact, the unconstrained and the constraint problems have the same minima, but we cannot analyze it theoretically. So we call this augmented RBMLE. And this constraint set is basically a confidence interval, okay? All right, and what's the performance? it has square root of t order performance, which is again shares its optimal regret order shared with other policies. Now this is how it performs. We've done setting on all the systems that have been reported in the literature. So this is a Boeing 747 model. Here's RBMLE. Here are some other policies. Okay, Thompson sampling, optimism in the face of uncertainty, etc. Now this is a log scale here, so the performance difference is quite a bit. And this is an unstable Laplacian. This is some other systems, some large transient dynamics. In all cases, RBMLE seems to do pretty well. And the close contenders are actually a policy that also goes back 50 years called input perturbation. So for a long, it has always been known that we've known for a long time that you have closed loop identifiability. Basically, once the parameter starts converging, you start getting information on the system. So what you can do is you can actually add little randomness to your actions, and that will excite other modes and you can learn information about it. And that's called information perturbation. So that also studied a lot in the 80s and 90s, but now people have examined it very carefully for regret, and it also seems to do pretty well. RBML is only very, 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 very marginally slightly better in these particular examples. Okay, so let me conclude. So this, the method, the basis is the fundamental limitation of closed loop identification leads to models with lower optimal rewards than possible for the true model. Hence, it counters this by biasing in favor of larger rewards. And it also embodies the philosophy of optimism in the face of uncertainty. It was established as long-term average reward optimum for a variety of systems decades ago. And recent re-examination shows that it has good theoretical performance and seems to have good empirically good performance. And it requires low computation per decision for bandit problems. And for these problems that we have examined. And we can also, there are a lot more other contexts that we could explore in the future. Okay, and with that, I'll stop, and thank you very much.
Is there any question? Perhaps a very naive one. So you have this this heuristic that seems to work very well in practice, but how do you find it? Do you have any heuristic to find the heuristic?
No. I gave you there's actually a very, this is not a wild guess. This is a very systematic design, which says, hey, listen, the fundamental problem is when you are trying to identify the behavior of a system, when that system is already under closed loop, then all you can ever determine is how the system is behaving under a particular closed loop control law. But you cannot identify what its behavior would be under some other control law that's not being applied, right? So that's closed loop identification. And closed loop identification leads to an equivalence between your imagined system and the true system under your imagined optimal control law. Okay, and it's from this it follows that you have to have a bias in terms of your optimal reward things, and from this we said, okay, let us then bias it. Bias it in favor. So it's specifically directed to solving a special quantitative problem, and we choose the exact right balance so that we don't damage the estimator while still keeping this trying to reverse the inequality. So I wouldn't say it's a heuristic. It's designed to solve a particular issue that arises.
I see. Thanks.
Mm-hmm.
Yes, Philippe, another question?
An even more naive question. what happens if your optimal model, your optimal...
But I cannot hear what you're saying.
I will repeat the question.
Okay. What happens if your optimal parameter does not belong to the set theta?
What happens? What happens if the optimal parameter does not belong to the set theta?
Beautiful question. So yeah, so this is what in the 90s, in adaptive control, we spent a lot of time looking at what we call this notion of robust adaptive control. So this assumption that the true system falls in your model class, that's violated. We were concerned at that point from an engineering context, because most control laws are designed in a linear approximation of the system. Okay, so that's why linear control theory is so widely used. But it's always been known that a finite dimensional model is never exactly correct. I mean, even if you have a flexible beam, it has infinite modes of vibration, right? So a finite dimensional model will only model a few modes. And now if you apply control which excites these other high frequency modes, then you can become unstable. So this can happen with a flexible space structure, aircraft, whatever. So people were always interested in showing design an adaptive controller which does well with respect to finite dimensional approximation of the system, but it should be robust in the sense that it is stable for these unmodeled dynamics. And it turned out that even in the case of linear systems, they're described by transfer functions as rational transfer functions, right? If they're finite dimensional. But if it's infinite dimensional, then it's kind of an irrational numerator denominator, because I mean you have infinite number of modes, right? So the right topology turns out in the space of transfer function is what is called the graph topology. So people were trying to show that stability is continuous in the graph topology and it's optimal for a finite dimensional representation. So we did that, and we published papers on that in the adaptive control context in the 90s. However, we haven't done it in the current era. So what has happened right now in reinforcement learning is that people have zeroed in on regret. So they've said, okay, let's look at the loss function under the assumption that the model can be fitted exactly, but what's the lowest you can drive the loss function down to? That's log t. But they've not yet gone to this issue of what if the model falls outside the set. So, but I think the field will go to that issue also, because if you're going to start looking at Boeing 747 and so on, you're going to have to worry about things like that. So I think that'll be the next phase. But most people are not aware of the work that has been done in the field in adaptive control. So this will have to be introduced into the field, I believe. Yeah.
Thank you. Any further question on the bridge?
Thank you.
No? Well, thank you very much.